Aluminum is everywhere, inside your phone, holding up skyscrapers, flying overhead in airplanes, and keeping your soda cold. It's one of the most versatile metals on the planet, and every day factories churn out around 200,000 tons to meet global demand. But before aluminum becomes part of your daily life, it starts as a reddish rock called bauxite, buried deep beneath forests and topsoil. At major operations like Alcoa's Australian mine, crews extract about 23 million tons of bauxite each year, over 2 million tons every month. Getting to this ore means stripping away huge stretches of land, raising big questions about the trade-offs between progress and environmental impact. The journey begins with a series of controlled blasts that shatter the earth and set the stage for the heavy machinery to move in. If you're enjoying the story so far, give the video a like, hit subscribe for more deep dives like this, and drop a comment telling us where you're watching from. We'd love to hear from you. Instead of explosions, the first thing you notice at a bauxite mine is the sheer scale of the operation. Bulldozers clear away forests and topsoil, making way for access roads and exposing the Earth's crust. This step is necessary to reach the bauxite deposits, but it's also the point where the environmental impact begins. Land is stripped bare, and ecosystems are disrupted. The reddish ore hidden below is what mining crews are after, and getting to it is all about efficiency and precision. Bauxite itself doesn't look like much. It's a dull, red, clay-like rock, nothing like the finished aluminum you see in everyday products. But inside this ore is aluminum oxide, the essential ingredient for making aluminum. On average, the industry needs about 4 tons of bauxite to produce just 1 ton of aluminum, so mining operations have to work at a massive scale. At the world's largest mines, like Alcoa's Huntly mine in Australia, crews extract around 23 million tons of bauxite every year to feed the global aluminum industry. To free the bauxite from the earth, mining teams first drill a grid of holes into the exposed ore. Into these holes, they load ammonium nitrate-based explosives, powerful but carefully controlled. When detonated, these charges break up the hard ground and loosen the bauxite, making it easier to collect. Each blast at a place like Huntly can clear 2 hectares of land and release up to 100,000 tons of ore. This method is fast and effective, but it leaves a visible mark on the landscape and generates plenty of debate about the long-term environmental costs. Once the ore is fragmented, heavy machinery moves in. Excavators with massive buckets scoop up the broken rock, while front-end loaders and dozers clear away what's called the overburden, the layer of earth and rock that covered the bauxite. Haul trucks, some weighing over 400 tons when loaded, ferry the ore to collection points. Watching these machines work is like seeing a carefully choreographed routine, each vehicle moving with purpose to keep the operation running smoothly. The next step is all about logistics. The bauxite is sorted and tested for quality right at the mine. Quality control teams sample the ore to make sure it meets the standards required for refining. From there, conveyor belts or rail lines take over, moving the sorted ore to stockpiles or directly to processing facilities. Some of these conveyor belts stretch for miles, carrying thousands of tons of bauxite every day. This setup keeps the supply chain running, ensuring that refineries always have a steady flow of raw material to work with. Managing the sheer volume of material is a challenge in itself. At major mines, stockpiling is essential. Ore is often stored in large, organized mounds before being loaded into trains or ship containers. These containers are sealed to prevent loss and contamination, then shipped off to processing plants, sometimes hundreds of miles away. This constant movement is what keeps the global aluminum industry supplied and operating at full speed. But mining bauxite isn't just about digging and hauling. Each step reshapes the land, leaving behind open pits and changing the local environment. Mining companies point to land rehabilitation programs, where mined land is restored and replanted. But there's always tension between economic demand and environmental stewardship. The scars left behind are a reminder of the trade-offs made to keep up with aluminum demand. And the environmental questions don't end at the mine. Once the bauxite reaches the refinery, it faces chemical processing that creates its own set of challenges. A major one is dealing with red mud, the leftover byproduct from extracting aluminum oxide. This waste has to be stored or repurposed, and managing it safely is a huge issue for the industry. So, the journey from Earth to aluminum starts with a massive, coordinated effort, clearing land, blasting rock, sorting ore, and moving it across huge distances. All this work is just to get the raw material ready for its next transformation. Up next, let's see what happens when this rough, red rock enters the refinery and begins its chemical journey toward becoming the white powder that makes aluminum possible. Inside the refinery, the transformation of bauxite continues with the Bayer process, a chemical method that changed everything for aluminum production. Carl Bayer's 19th century breakthrough made it possible to extract pure alumina from bauxite, turning aluminum from an expensive curiosity into something the world now relies on for packaging, transportation, and construction. The process starts by taking that rough, red bauxite and crushing it down into a fine powder. Breaking the ore up like this isn't just for show. It's all about increasing the surface area so the next step works better. The finer the bauxite, the more efficiently it reacts. Once the ore is ground, it's mixed with hot sodium hydroxide under pressure. This step dissolves the aluminum oxide out of the bauxite, leaving behind impurities like iron oxide and silica, which don't react with the sodium hydroxide at all. What you get after this reaction is a thick slurry, a messy reddish soup. The valuable part is the dissolved aluminum oxide in the liquid, but first the leftovers need to be removed. The mixture is filtered, separating out the solid impurities. These impurities, mostly iron-rich and known as red mud, pile up fast. For every ton of alumina produced, the industry generates about 2 tons of this red mud, highlighting just how much waste comes with refining bauxite. Red mud is a huge challenge. It's caustic, takes up space, and needs to be carefully managed to avoid environmental problems. Once the red mud is out of the way, the remaining liquid, called sodium aluminate, holds the dissolved aluminum oxide. This liquid is cooled in a controlled way, and as it cools, tiny crystals of aluminum hydroxide start to form. Picture these crystals growing, slowly turning the once murky liquid into something that looks almost like a snow globe. Getting the temperature and concentration just right is key. If it's off, the crystals won't form properly. After the crystals have grown big enough, they're separated from the leftover liquid and washed to remove any remaining traces of caustic soda. Then comes a crucial step: calcination. The crystals are fed into a kiln and heated to around 1000 degrees Celsius. This high heat drives off water, leaving behind pure alumina, a fine white powder that looks a bit like sugar. It's hard to believe that something so clean and uniform comes from the muddy, messy bauxite that started the whole process. This is the stage where the Bayer process really earns its reputation. It's not flashy, but it's the bridge that takes raw earth and turns it into something ready for the next big transformation. The process is efficient at pulling out the useful aluminum oxide, but the environmental cost of red mud disposal is always looming in the background. Research continues into ways to reuse or neutralize red mud, but the scale of the problem is massive, and the industry hasn't solved it yet. It's easy to overlook just how much chemistry and engineering go into producing alumina. The Bayer process is a careful balancing act, crushing, dissolving, filtering, crystallizing, and heating, all on a scale that supplies the entire world's aluminum needs. Every step is designed to maximize yield and minimize impurities, making sure the alumina is pure enough for what comes next. But that fine white powder is just the halfway point. What happens when we unleash high-voltage electricity on it? The next phase is where chemistry meets engineering, and the transformation is as dramatic as it gets. Step into an aluminum smelter, and you'll find a world built for extremes. Here, alumina, the fine white powder from the refinery, meets the Hall-Heroult process. This is where chemistry and engineering combine to turn powder into glowing, molten metal. The process begins with alumina being added to massive electrolytic cells, or pots, each lined with carbon. On its own, alumina's melting point is over 2,000 degrees Celsius, which would be impossible to handle on an industrial scale. To make things practical, engineers dissolve the alumina in molten cryolite. Cryolite is a rare mineral, but here it acts as a solvent, bringing the melting point down to about 950 degrees Celsius. That's still hot enough to melt rock, but now it's manageable with the right equipment. Once the alumina dissolves, the real transformation starts. Huge carbon anodes are lowered into the cell, and a heavy electric current is sent through the mixture. This isn't just a trickle of electricity, it's a flood. Some smelters draw as much power as a city of 300,000 homes, making electricity the single biggest operating cost. That's why you'll often find these plants right next to hydroelectric dams, where renewable energy is both abundant and affordable. Inside each cell, the electric current splits the aluminum oxide into its elements. The aluminum atoms break free and, being denser than the surrounding liquid, sink to the bottom as molten aluminum. The oxygen atoms released in the process don't just vanish, they react with the carbon anodes to produce carbon dioxide gas. This step is a major source of emissions for the industry, and it's one reason why researchers are now working on carbon-free anodes that could cut these emissions dramatically in the future. The smelting process runs around the clock. Fresh alumina is added to the cells as needed, while molten aluminum is siphoned off every 36 hours or so using vacuum pumping systems. The metal is collected at around 950 degrees Celsius and poured into insulated transport crucibles, designed to keep it hot and ready for the next stage. Each cell can produce several tons of molten aluminum each day, and with hundreds of pots in a single plant, the scale is hard to overstate. As you look around the plant, you'll notice the constant hum of electrical equipment and the glow of orange metal at the bottom of each cell. Workers in protective gear move carefully through the heat, monitoring levels and making adjustments to keep the process running smoothly. The environment is all about control. Temperature, chemistry, and timing all have to be just right. The Hall-Heroult process, first developed independently by Charles Hall and Paul Heroult in 1886, changed the game for aluminum production. Before their discovery, aluminum was rare and costly, reserved for special uses. This electrolytic method made mass production possible, turning aluminum into a material for the modern world. But even with all this progress, the environmental cost is never far from mind. The energy demands are huge, and the release of carbon dioxide at the anodes is a challenge the industry is working to solve. Many smelters now run on hydroelectric power to reduce their carbon footprint, and ongoing research into alternative anode materials holds promise for cleaner production in the years ahead. Once that shimmering pool of orange metal forms, it's time to shape it, and that's where casting adds a whole new dimension. The metal is ready to leave the world of high heat and electricity behind, setting the stage for its transformation into solid, usable forms. Turning molten aluminum into something solid and useful starts with casting. Molten metal is drawn from the smelter and poured into large ingot molds, each designed to give aluminum its first definitive shape. Temperature control is crucial. Cooling the metal too quickly or unevenly can cause cracks or structural flaws. Inside the casting facility, systems monitor the rate at which the aluminum solidifies, making sure the metal hardens evenly. What comes out are giant rectangular slabs, each weighing several tons with a smooth, solid surface that's ready for the next step. After leaving the molds, these ingots need a bit of prep before they're ready to be turned into the thin, flexible sheets you see in everyday products. First, the outer layers are shaved off to remove surface impurities and imperfections. This scalping step leaves behind a clean, mirror-like finish. Right after, the ingots are preheated to about 500 degrees Celsius. This heating makes the aluminum pliable enough for the rolling mills, preventing cracks and making sure the metal can be shaped without waste. Now, it's time for the real transformation. The prepped ingots move to reversing mills, where the heavy machinery takes over. Imagine two massive 7,000 horsepower motors powering rollers that squeeze and flatten each slab. The aluminum starts out thick and tough, but with each pass through the rollers, it gets thinner and longer. The process is repeated several times, and you can see the metal stretch out, changing from a chunky block into a broad, gleaming sheet. Once the aluminum is the right thickness, it's cooled to between 200 and 300 degrees Fahrenheit. This sets things up for cold rolling, which is all about refining the metal's final properties. Cold rolling uses smaller, more precise rollers to get the sheets down to their exact thickness and to give the metal extra strength and flexibility. The sheets are then wound into coils. Each one can stretch over a mile when unrolled. These coils are easy to handle, transport, and store, and they're ready for whatever comes next. The next stop is the fabrication department. Here, each coil is labeled with a unique code for quality control, then inspected, trimmed, and wound onto spools. This step ensures that every batch of aluminum meets strict standards before it's shipped out. Whether the coil is destined for a beverage can, an airplane wing, or siding for a building, the quality checks make sure it's up to the job. Aluminum's versatility really starts to show at this stage. Rolled sheets and coils can be cut, stamped, or shaped into thousands of different products. The metal's light weight and resistance to corrosion make it a favorite in industries ranging from construction to transportation. It's strong enough for car panels, flexible enough for foil, and clean enough for food packaging. Plus, aluminum doesn't lose its strength when it's shaped into complex forms, so manufacturers have a lot of freedom to innovate. What's also impressive is how the production process is designed to minimize waste. Any trimmed edges or scraps left over from rolling and cutting are collected and sent back for remelting. This closed-loop approach keeps material loss low and helps keep costs down. By the time the finished aluminum leaves the factory, it's ready to become part of daily life. You'll find it in the can you drink from, the car you drive, the window frames in your home, and the electronics you use every day. Each product starts with those massive ingots and ends up as something familiar and essential. The journey from bauxite to rolled aluminum is a story of engineering, precision, and adaptability. But the story doesn't end here. There's another chapter that gives aluminum an edge over almost every other material out there, one that's all about endless possibility and sustainability. Imagine saving an entire year's worth of household power with just 1 ton of recycled metal. That's the kind of impact aluminum recycling has. Every time you toss an empty soda can into the recycling bin, you're helping conserve energy, reduce emissions, and cut down on the need for new raw material. Aluminum stands out among metals because it can be recycled endlessly without losing any of its strength or quality. This means the can you recycle today could come back as part of a car, an airplane frame, or even another can, completely indistinguishable from aluminum made straight from bauxite. The recycling process is straightforward but powerful. It starts with collecting scrap aluminum from all sorts of sources: cans, old car parts, window frames, and more. After sorting and cleaning to remove any paint, plastic, or other contaminants, the scrap is melted in a furnace at about 660 degrees Celsius. This molten metal is then cast into new ingots or slabs, just like those made from freshly mined bauxite. These can be rolled, shaped, or processed into new products, ready for another round of use. There's no loss of quality, which is why recycled aluminum is trusted in demanding applications, from aerospace components to electric vehicles. One of the biggest advantages of aluminum recycling is its efficiency. Making aluminum from scratch is energy-intensive, but recycling uses only about 5% of the energy needed to produce new metal from ore. That's a huge saving, not just in electricity, but in resources and emissions too. Recycling a single ton of aluminum saves enough energy to power a home for a year. Multiply that by the millions of tons recycled every year, and the benefits add up fast. This efficiency is why around 75% of all aluminum ever produced is still in use today, circulating through products and industries around the world. Recycling aluminum also means less need for new bauxite mining. This closes the loop on the environmental impacts discussed earlier. Fewer forests cleared, less topsoil disturbed, and a smaller footprint from mining operations. Every ton of recycled aluminum is a ton less that needs to be dug from the ground, making recycling a direct way to protect natural resources and habitats. The turnaround time is impressive too. Beverage cans, one of the most visible forms of recycled aluminum, can make it back onto store shelves as new cans in as little as 60 days. But recycling isn't limited to cans. Large amounts of scrap are used in car manufacturing, airplane construction, building materials, and electronics. No matter where it ends up, recycled aluminum performs just as well as primary metal, making it a favorite in industries that demand high performance and reliability. Aluminum's recyclability is also a model for how materials can keep circulating through the economy without degrading. Unlike plastics, which lose quality with each cycle, aluminum remains strong and workable. This means it can be reused again and again, supporting a truly circular economy. It's a material that doesn't wear out, even after decades of melting, reforming, and reshaping. Looking ahead, aluminum is set to play a growing role in green technology. Its lightweight and strength make it essential for electric vehicles, which need to be as efficient as possible. It's also critical in renewable energy systems. Think wind turbines and solar panel frames. Even in space exploration, aluminum's unique properties allow for lightweight, durable structures that can withstand harsh conditions, with recycled metal increasingly used in these high-tech fields. The industry isn't stopping here. Many companies are now investing in renewable energy to power recycling and production facilities, aiming for a future where aluminum production has a minimal environmental footprint. Some are even developing zero-carbon smelting technologies, hoping to eliminate emissions from the process entirely. These efforts point toward a future where aluminum not only supports sustainability through recycling but also through clean, innovative production methods. Aluminum's ability to be recycled over and over, its energy savings, and its vital role in everything from packaging to advanced engineering all highlight just how important this metal is. Its journey doesn't end with a single use. It keeps coming back, supporting progress while reducing impact. When you look around at the aluminum in your daily life, you're seeing a material that's been shaped by decades of innovation and a commitment to sustainability. And that journey from raw ore to endless reuse is just one example of what's possible when human ingenuity meets the challenges of our time. Aluminum's path from raw bauxite to infinitely recyclable metal shows how far resource management and engineering have come. It's more than just a material. It's proof that we can create products that last, get reused, and help cut down on waste. The next time you pick up a soda can, remember that it could have already lived many lives, maybe as part of a car or a building, and it's ready to be recycled again without losing any quality. Now, we want to hear from you. Tell us in the comments which everyday materials hidden journey you'd like us to explore next.